Okay, so fun with math. So I call this exercise solve total triangle. And what we're going to do is just solve a triangle, but the key here is you can only use sine, cos, and tan once to solve the triangle. So just to get into calculator use a little bit here. So now I have a Sharp EL520XT. This is the way it works for this model. If you have a different kind of model, then you're going to have to figure that one out for yourself. But if you have this model, this is the way it works. So to expose the ratio, and again the ratio of the sides, talking about from the previous lesson, from the trigonometry intro lesson, you hit sine degree, so the degree, which is say 30 degrees, so you hit sine 30, and then equals, and that's going to expose the ratio. For example, right here, sine 30 degrees equals, and then the answer will give you 0.5. If you want to convert the ratio to an angle, there's just one extra step here. So you would hit second function, your sine, cos, or tan function, input the ratio, and then equals. For example, second function, sine 0.5 equals, and the answer you'll get will be 30. So that's just a little lesson on calculators, or that model of calculator. So the hypotenuse will always be the same and will always be the largest magnitude. What I mean by the same is it will always be the largest magnitude. So the opposite is relative to the angle, and the adjacent is relative to the angle. For example, here, if I'm looking at this angle right here, kind of just like an eyeball looking down the other way, relative to the angle, this is opposite the angle, this segment here, and right here the adjacent is, or this side is adjacent to the angle. Whereas if we're dealing with this angle, the segment opposite becomes this side, and the segment adjacent becomes this side. And the hypotenuse will always be the hypotenuse. So let's start off. If we have, so we got sine, cos, and tan is, we're only allowed to use once. Now I can give you any value. I can give you the angle and one side. I'll always give you two values, so whatever it is. In this case, we have the hypotenuse is 7 and this segment here is 3. So if we use our sine function, so right here we have, so to this angle, we have a 3. If we take this angle, 3 is opposite, and we have the hypotenuse. Again, we're looking at SOHCAHTOA here. So for the sine, S for sine, C for cos, T for tan. So the sine of the angle theta here, is relative to opposite over hypotenuse. Now remember, sine will always give you a decimal, and the only way to achieve a decimal is to stack the lesser on top of the greater. As long as the numerator is smaller than the denominator, you will always get a decimal. So you have sine of angle theta is equal to the ratio of 3 to 7, which equals 0.428. So we want to convert the ratio, because this is a ratio, right? Meaning this segment right here is 42.8% of the hypotenuse. Second function, sine, our ratio is going to give us roughly 25.37 degrees. So now we have 25 25.37 degrees. So now we'll call that 25.4 degrees for the sake of the rest of the calculation. So if 25.37, if I take this value, so now we have one of the angles accounted for, and we have one segment, and we have the hypotenuse. So we have a couple choices here. So say for example here, we got 25.37, we have the angle. This is the adjacent to the angle, and we also have the hypotenuse. So we can use the cosine if we like. We have the adjacent we're looking for, but we have the angle, and we do have the hypotenuse. So the cos of angle 25.37 is adjacent over height, and what we'll do is a little bit of math here. I'm not going to spend some time, but I've referenced the 2 times 3 equals 6 scenario quite a few times already. So we'll just switch everything around. So the adjacent is equal to the hypotenuse times the cos of 25.37, which is going to give us 6.32. Now again, the cos is always going to be between 0 and 1 or 1 and 0. So you'll always have a decimal. And the adjacent segment is going to be less. These two segments are always going to be less than the hypotenuse. So if you start thinking in terms of relationships, the formulas actually go away. When you divide by a decimal, the number goes up. When you multiply by a decimal, the number goes down. And the sine and cos will always give you a decimal. So if you stick them as the denominator, right, the number will always go up. Here, you're looking for the adjacent. The relationship with cos is to the hypotenuse. So you're going to use the hypotenuse to find the adjacent. Well, the adjacent is not going to be larger. It's going to be smaller. And the cos will always give you a decimal. And that pretty much tells you what you need to do. It's just you have to think in those terms. And the formulas will just disappear because the relationships, you'll be able to see the relationships. I can't stress how important that is. So we have 6.32. So we carry on. We got 6.32. So now we have each side accounted for, and we're looking for this angle. So now we have a couple options here. So we have the tan of angle theta. We got opposite over adjacent. So if we're looking for this angle relative to this angle, 6.32 is the opposite. This becomes the adjacent. Now, when it comes into the tan, remember that adjacent here is the reference point. So what you're looking at here is this segment is the reference point, and what you're tracking down is this segment right here. It stands to reason that when you bring up the ratio, this is the smaller segment, this is the larger segment. So anything past a 45 degree is going to be a number larger than 1. So just be conscious of what it is you're tracking down and the numbers that you're punching in and the numbers that you're looking at. If you're conscious of this relationship, you'll know that this number is going to be larger than 1. So the tan of angle theta is opposite over adjacent, which means 6.3 divided by 3, 2.1. It makes sense. This is not the scale, by the way, but either way. 2.1, second function, tan, gives you 64.6 degrees. And that finishes off that first exercise. So let's try that again. So I'm just going to change the angle here. So we got, you can only use sine, cos, and tan once. So we have 30 degrees. We have 7. We have 3. Again, we have a couple options here. Sine, cos, and tan can only be used once. So if we take, what do we got here? So if we take, get rid of that. So 30 degrees, 7 as hypotenuse. Let's see what we got. we got 30 degrees, we got 7, so that sort of limits us. We're going to have to solve for the hypotenuse here. Actually, that's not true. We could solve for the adjacent, but I believe the opposite is what I was going for there. So the sine of 30 degrees equals opposite over 7. So the opposite equals 7 times, again, is going to be a decimal. Sine of 30 degrees gives us 3.5. So we got 3.5. Now we have a couple options again. So we have the cos. We can use the cos of angle theta. So now right here, we track down the angle. We have the adjacent. We have the hypotenuse. And again, it's going to have to be a decimal. So we got 3.5 over 7 gives us 0.5. Makes sense if you think about the relationships right there. Second function, cos, gives us 60 degrees. And if we just finish this off here, tan, 30 degrees, so we'll use the tan here. We just want to track down this segment, so it's opposite over adjacent, or the ratio of opposite to adjacent. And it stands to reason that this number is going to be less, because this segment is now the adjacent, so you should be getting a decimal out of here. And when you divide by a decimal, this number is going up. So you have the tan of 30 degrees, which is going to be a decimal. So, and that gives us 6.06. So we have another triangle solved. So, if we just finish this off one more time, we have 70 degrees and 4. Now the thing about this exercise that I do have to remind everybody of is sine, cos, and tan have to be used. No a squared plus b squared equals c squared, none of that kind of stuff, and none of 90 minus 70 equals this angle. That's not going to work. I have to see the trigonomic expressions for these three. Nothing else is going to work. Even though I know it all works, but this isn't about a squared plus b squared. This isn't about reducing angles. This is about sine, cos, and tan. So, if we start off 70 and 4, now if you want to pause the video and try to solve this triangle for yourself, by all means. And anytime I'm doing the lesson, always feel free to pause and try things for yourself. Here we go. So we got the tan of 70 degrees. So I just switched it up a little bit. So notice I had this sequence here. So I just went the other way just to show you it doesn't really matter which way you go. So the tan, I have the adjacent here, the tan of 70 degrees. And again, this is the adjacent. So this is going to be larger than 170 degrees, anything over 45. So opposite equals 4 times the tan, going to give us 10.98. We go to the next one, the sine of angle 70 degrees. And again, you can use the same angle, right? That's not the problem. It's sine, cos, and tan that have to be different. So the sine is 70 degrees, because now we have the opposite, so we can track down the hypotenuse there. So the sine is 70 degrees. Again, it's going to be the decimal. So 10.98 is the opposite. That number has to go up. There's really no choice. And if you think about the relationship, there's really only one thing to do here. So the hypotenuse is going to be equal to 10.98 over the sine of 70, and that's going to be 11.69. And just to finish it off, we have the cos of the angle. So we're going to track down the angle, and we can use the adjacent and the hypotenuse. And again, it has to be a decimal, so there's only one way to stack these numbers. The lesser to over the greater, 0.93, second function, cos, gives us 20 degrees. So I've made a few little highlights here, right? The opposite, 2.7, the length of the adjacent, larger than 45. This is a decimal, 93%. Cos is a decimal. The adjacent segment is 93%. And that is it for solve total triangle.